I'll elaborate a little bit on the synergistic reconstruction approaches. Yeah, well, can somebody confirm you're seeing the full screen presentation, please?
Yes, we see it, Kris.
Yeah. Okay, so thank you. The approach that Andrew explained to you at the end is an alternating approach, as he said. So you might have two images that you want to reconstruct. As an example, well, you can reconstruct X, where you know Y, and you use Y as side information or as a guided reconstruction, and then you go back to reconstructing Y once you know X, or maybe there's a Z as well, then you just have a third one over here. So that's one approach. And so this approach implies that any guided method that you have, you can extend to the synergistic case. But obviously, that doesn't mean that it will work very well. You have to be careful, not only with how you set up your alternating scheme, but also which prior you use. Yeah, that should be obvious. So this is one way of doing things. The other way, main way, I think that there are quite a few different ways, but the other main way that we wanted to discuss is what I call joint optimization. So Andrew already gave you a very large objective function at the very end. So I'll elaborate a little bit on that. So if you say I have to do a reconstruction of two images, I've written it here with MRMPET just to allow you to look at the PSMR presentation that is mentioned on the HackMD website. So I've just copied a few slides from there, but there is more information there. Then I've changed a few things near the end. So this would be two objective functions that you have, and you can add them together. And each of those might have two similarity data fidelity terms and two regularization terms. But so the trick is, can we add another term that couples the two or three or whatever number you have together? And so what Andrew showed you was one way to do this. However, it was evolving over iterations. And so some people, in some sense, don't like that, and they came up with prior formulations that don't need it. Which of these two is the better one? And it's entirely problem dependent and application dependent. Okay, so the first, probably, I think oldest approach is what's called joint total variation. I think by now you know what total variation is. Let's suppose you forget about this term over here. You take the image gradient in X, Y, and maybe Z if it's a three-dimensional image, and just take the L2 norm of it. And then you sum that over all the pixels. Now, if you do it with joint total variation, you put the sum inside the square root. If you put square root plus another square root, the two image modalities are not coupled. So that would just be sometimes called factorial total variation, or I mean, terminology on that is not so established, I guess, but you need to have the square root on top of the whole thing to couple things together, right? Now, it's maybe not so, it's clear that this is going to try and make flat regions. It's maybe not so obvious that it encourages edges to be in the same place, but if you remember that total variation encourages sparsity in the image or in the coefficients that you estimate, then you will also have sparsity in the joint images coefficients. So, or in this case, gradients. So that means it's going to put gradients as much to zero as possible. But if they are not zero, it's going to put them in the same place. However, this approach is independent of orientation. That's not so ideal. because clearly edge orientation is important. And I think there are historically two approaches to look at this. So one says it's called parallel level sets. So level set is like a contour plot of the image, and you can look at the gradients with that are orthogonal to the level sets of the two sets of images. And clearly, if you have an orientation difference of your two gradients, that is not desirable. And so Matthias Erhardt encoded this by adding a penalty that depends on the angle between the two gradients. Obviously, it encourages regions to be flat, and it encourages edges to be parallel now, which is why it's called parallel level sets. However, this prior turned out to be rather difficult because it is not a convex prior in the two different modalities. It's convex in each of them, but not in both. And so you can have local minima and you can have flips in image intensities and so on. So that's not ideal. You have to take care of that in other ways. So other people came up with something which is more related to the total variation, sometimes called total nuclear variation. And what that does, it uses the nuclear norm of the Jacobian. So you stack all your image gradients for every voxel. Yes, you stack them all together into one matrix, and then you compute the nuclear norm, which is the sum of all the singular values. So now you need to be able to compute singular values and so on. But we can do that, and actually this is implemented in CIL. So this does exactly the same conceptually, because if your edges are parallel, your matrix is going to have zero singular value. So therefore, your nuclear norm is going to be smaller than when they are not parallel. However, this prior is convex in both modalities. So it is maybe therefore easier for an optimization algorithm to handle. Okay, so those, I believe, are the two main ones. There are variations on all of these, and you can't do things with wavelets and so on, but or curvelets. But I think these give you the main idea, and these we do have in CIL. Okay, so I have now a joint prior that tries to put some structural similarity between the different images that you have. The question is now, how are you going to optimize this? And actually, what most people are doing is they're going to alternate anyway. So what they're saying is, I'm going to find a maximum. I'm freeze one image. I'm going to try and find the other image. I've written it as maximization over here. Then you freeze that one, and you just flip the order around. So this is sometimes called grouped coordinates. Well, actually ascent if you do maximization. And if you do maximization, this is an approach that will converge theoretically under very mild assumptions. However, nobody really wants to do maximization here because that's too computationally expensive, and then you get into difficulties of proving convergence. But in practice, this is the approach that many other people do. Now, you could say, no, instead, I'm just going to say, I have a very large function here, this one, and I'm going to throw it into my optimizer and maybe split off the regularizers and so on with any of the algorithms that we have. And so this can be done in CIL as well. However, most people don't follow this particular approach, and that is the one optimizer thing. And that is because often your images or data have very different scales, and if the scale of a PET image is a wildly different thing from MR, and in MR different sequences might have different scales as well. It's probably less of an issue once you do dual energy CT or things like that, but still it's not not a very easy problem, because you might have ill conditioning in certain in scales of the image. So often people do it alternating. Now, then obviously, once you say, I'm doing it alternating, then you are very close to the approach that Andrew was discussing at the very beginning. Yes, so the two approaches are very much related. I guess the only difference then is that here we don't modify the prior based on the previous image. The priors remain fixed. It's just that we do the alternating optimization. We discussed the equal sampling and so on, but you can put resampling in and then just write your objective function in terms of resampled functions. It's doable and actually can be implemented in SIRF together with CIL. Clearly, all of this is going to fail dramatically if your images are not registered. So for dual energy CT or so, where the acquisitions are done at the same time, that is not a problem. For any sequential acquisition, this is potentially disastrous. So those are things that you have to take care of. And just a final note is that really, once you have a synergistic prior like this, a multimodality prior, you can obviously boil it down to a guided prior as well. So before, at the very beginning, we said, as soon as you have a guided prior, you can build a synergistic one by alternating. Now the other way around, as soon as you have a synergistic prior, you can build a guided reconstruction as well, just by freezing the other image or images. And that can be quite useful. Okay, so that's what I wanted to say on the different approaches for synergistic reconstruction. Any questions people want to ask?
Kris, I got a good question. So you said the problem can be that the magnitudes of the two images, for example, pattern MR, can be very different. But I think the magnitude is not the real problem. I think the real problem is that, you know, optimizing a quadratic, for example, if you have a quadratic data fidelity term in MR, converges much faster compared to optimizing the Poisson log likelihood. And I think this is the real problem.
Yeah, so I mean that's certainly true. It's often easier to think about ill conditioning in terms of scale of the image. If you do a gradient descent type of algorithm and you just scale one image with a factor 100, it's going to change your gradient, right? And so in that sense, you have to think very carefully about the scale of the images. But clearly, you are 100% correct that it's actually the objective function itself and the sum of the objective functions that determines which directions you should be taking. Yes, and that is not an easy problem. So yeah, you need to, I think if you do joint optimization with one update, then you need to think very hard about preconditioning. Otherwise, it's not going to work.
Okay, thanks.
Okay, so we have some notebooks that try and get you familiar with some of these concepts, and the notebooks they implement some of these methods or try and suggest to you how you implement them, and they also often have extensions to let you think about some of the issues that I have here on the slide, right? So there are examples there where it says, okay, as opposed to using a normal PET and MR, for instance, with Boucher prior, now assume that your MR is a bit misregistered, and what is the effect going to be, or can you put in a registration step to try and resolve this? So we have sort of two sets of notebooks. I'm going to first show you a little bit on what we have on SIRF, on synergistic reconstructions, and then Vangelis is going to talk about the CIL ones, and the CIL ones include one in SIRF, just to make life interesting. So let me show you. Just a README for, so this is the synergistic directory of the SIRF exercises. So I think you can just have a look at the README there, and the link is provided on HackMD. Obviously, the first notebook there is something that you hopefully have looked at last week. If not, you should probably do it now. That just implements gradient descent or ascent for the 3 different modalities and shows you the similarity in the code that you can use. And because the code is similar, it also makes life much easier to implement any of the methods that we have talked about earlier. Then there are some notebooks here to generate example data used in the other SIRF notebooks. And the example data is based on the brainweb. Again, it generates some PET and MR data. And it's largely a copy of the brainweb tools that you have seen before. It's probably a little bit less clean because it's a bit older, but it's more or less the same. The only difference is that it also adds some specific features in the PET data, for instance, such that you have a lesion in the PET data that is not in the MR, because as Andrew explained, the big issue with all of these methods is what happens if you don't have a match between the different images that you reconstruct. And so that allows you to explore that a little bit. So that's this notebook there. Then there is a notebook that just implements the MapEM method using the Boucher prior. So this is an extension of the MapEM notebook from last week, except it calls the Boucher prior here, and it encourages you to evaluate the difference between the two. There is the dual PET one that then says, okay, now that you've been able to do this, you can also set it up for reconstruction, where you can alternate between 2 reconstructions of PET data. So suppose you have 2 different traces. You can now say, okay, I'm going to reconstruct one tracer where I use the other one as guide, and then flip the roles around. So it does that with the Boucher prior because you have that implemented. I don't think the Boucher prior is the best prior to set up synergistic reconstruction, really. But once you've done that, you can also extend it to other priors, clearly. And by the way, the code there it relies on a prior class that was contributed to SIRF from the people in Andrew's group. So the method that he's explained to you for the Gaussian weights is available there as well. So you can implement that instead, as opposed to the Boucher prior. Then there is also a notebook that looks at the hybrid kernel method. And what that notebook does is it doesn't ask you to implement it, because that would probably be a little bit hard. So it uses it as a black box, but it shows you how you could evaluate all the different parameters that there are in prior like this. Do a little bit of a search, and then encourages you to look at what is the influence of those parameters. So that this is more of a practical notebook. How would you do such a thing? All of these say, well, what happens with misalignment? And the joint TV for MR, I'm going to leave to Vangelis. So do have a look here. That is probably, there's a fair amount of overlap between all of those. I think if you've done one, you've already learned a lot, and then you can maybe have a look at the others. So some of them have a lot of material, others more or less have only questions, but there are then some suggest solutions in a different directory that set up most of the things for you to do the, well, solve the exercise. Okay, so I'll stop sharing now. Any questions in the meantime?
I have a question about the size of the kernel. The smoothness that you get, or the information you get from the kernel where you calculate the similarity, can it depend on the size of the kernel that you choose, or there is a best suggestion?
It most definitely will depend on the size of the kernel, and you tend to have a trade-off there between computation time. A larger kernel that you use, obviously, the more you will need to calculate. But then also, on the other hand, a larger kernel can try and assemble more information. So a larger patch gives you more information. You then need to be careful that your method doesn't over smooth over the patch. So I mean, all of these methods start to have a fair amount of parameters, and there is no golden criteria, unfortunately, that tells you, oh, I do this particular application, you should use a kernel of 5 by 5 by 5, and for that one it's 3 by 3 by 3. You have to do these experiments, and you have to try and find out for your data and your application, and that is obviously very much related to all the deep learning things. So one of the first things that people did with deep learning, I think, in the image reconstruction context, is to say, I am going to try and learn the parameters, but I'm going to learn them such that if I give some input, I find a reasonable optimal value. So you first do a training where you find optimal parameters on your data set, so that you can now give it your actual data, and it will suggest the approximately optimal parameters for you.